There we are. So I tried my best in getting the slides to show. This worked the first place. I had more troubles unmuting the mic, but also this worked now. So I'm very happy to be here again to talk about a topic that at least I personally find quite interesting, but I also think it has some challenging and interesting aspects. So when we talk about computer science, usually we think of computers. A computer is something with a display and a keyboard and something behind it. And most of the computers that we are aware of would have more or less this look. But actually, if we just count by the numbers of CPUs, most of computers or most of CPUs are embedded somewhere. So they are not visible, they are in some devices. And so this makes out a great deal of computers active. And in the context of energy systems, I don't want to talk about the energy consumption of those devices right now, how to optimize this. This would be this first type of sustainability in computer science, but rather what we could use from those systems in order to get to a more sustainable use of resources. So sustainability with computer science, if I got the definitions right at the beginning. So the topic I would like to talk about is electric load disaggregation as a means for increasing energy awareness and reducing energy consumption. So currently we're using energy in various forms in our daily life, at work and via machines. And especially when the energy is not produced from renewable sources, this is a significant problem for sustainable living. So there are some times of the day where we actually have an energy surplus. So typically with a lot of photovoltaics around noon in summer, but now it's getting colder again. We have autumn and in a couple of months, we will have winter, and in winter times, we don't have that much sun, so we are back to using probably fossil fuels in some way or another. Also, throughout the year, we might have a very good average, but now in winter time, we really have the problem with using energy of a kind that we don't want to use too much again. So, what can we, as computer scientists, do to help? Apart from just turning off our computers and not using them. And in this talk, I basically want to address this question with the use of computers, smart meters, the proper algorithms and data sets. So when we talk about smart meters, you're probably aware that there has been a smart meter rollout. This was already started by the Energy Service Directive of the European Community in 2006 and another directive in 2009 that required the implementation of intelligent metering systems. And the idea was that such systems ought to be in place in 80% of electricity consumers by the end of 2020. So this is now a date in the past. Did we make it? No, because they were absolutely on plan until suddenly Corona struck and that threw them back, which is a bit odd because if you are anyway to be planned to finish by 2020, you might have done it already. But it was a bit slow, but now basically we have the smart meters in place and the number of electricity meters also required the to have standards for the communication with the smart meters for the data and everything. So this is still something that is in development. So if you have a smart meter at home, then depending on your provider, you might have different ways of accessing the smart meter data. But this is also a challenge, but this is a different challenge. But looking at the possibilities, so basically we moved from a meter like the one on the left side. Probably you still have some meters like those somewhere around. That's not too uncommon, but typically now in many households we find the smart meters that can look like the Meteoros meter that is shown here on the slide, but they can also look a little bit different. But in general, they have this display to show the current consumption, like also the old meters did. And they are measuring digitally your energy consumption and reporting it to the energy utility, to your energy provider, in order to provide the information for billing. So far, this is not a new feature. This is what the old meters also did. Just for the old meters, it was necessary to send somebody over to read them. And now with the new meters, they can transmit the information directly. But actually, the time when this is done, usually for the old meter, it was like once a year. And for the smart meters, depending on their configuration, they can report like one measurement every 15 minutes or every hour or every day, which is in all of those cases, it's much faster and much more frequent than for the traditional meters. And that means also that you can have a more timely information about your energy consumption and bills. Okay, doesn't make a difference. Anyway, we have to pay our bills sooner or later. But actually, the billing and the billing or the time when you get your energy bill has a huge impact on how much you're aware of your energy consumption. So, consumption information is connected to billing. So usually you check how much you have paid, how much you have paid last time, and this kind of gives you a signal, oh, I have consumed so much more energy, or I was now better than last year. So it paid off to like replace that old device, that old fridge I had, or whatever. Uh, but typically the bill comes much later than the consumption occurred. And even though you are typically paying a monthly bill, this is an estimated bill. So basically, on your consumption from the last year, there is an average used to basically define the value that you're going to pay each month, each month. And so if you look at the energy bill, it just tells you what you have consumed last year in average. Doesn't tell you what this new device that you just bought did with your energy bill for last month or so with the traditional meters. And if we would get this now more frequently, would that make a change? Has somebody looked into that, if that would be an advantage? And yes, when looking into strategies for domestic energy conservation, it has turned out that there are different ways of improving the overall energy consumption by just informing the customer about their consumption in a more detailed way. So there are different ways like energy audits, like analyzing the energy use and providing tips. Smart metering, just more frequent meter reading and reporting, which was implemented in Italy quite early with the smart meter rollout. Prepaid billing. So basically, you have to pay in advance, and then you are informed when you run out of your budget, which means that you have to think about your estimated energy consumption ahead. Adaptive tariff plans. This would be an incentive of user to operate in off-peak periods, as I explained already in the introduction. When we have a significant amount of photovoltaic produced power in our system, then we would like to shift energy consumption towards the time when we have a peak in photovoltaic production. And a motivation to do this would be to have different energy tariffs depending on the time of the day. And adaptive tariff plans, they are possible with smart meters. They are very difficult to realize without the smart meters because basically you need somehow to register for a certain consumption when it took place. So either you have 2 meters and 1 meter is used during daytime uh, or time around noon, and the other meter is used in the evening, and probably a third meter would be used at the weekend if you have 3 tariffs. But that would be a lot of effort, and you still need some kind of clocking device to switch. Or you have a smart meter that can just register a consumption with a certain time of the day, so that that you later or in real time can calculate the actual consumptions worth for this time, depending on the current tariff. And then another means would be persuasive interfaces, nudging, and also supporting users in understanding their energy usage. And basically, there is a wide range of possible energy savings, depending on different pieces of literature, reporting from estimated 3.8% up to more than 12% with a tailored appliance level feedback. In general, you can say that the more detailed your feedback, the better. So one thing would be to increase the frequency. So you just get an information about your energy consumption every day. You could even increase it further, but probably that would not be so convenient that, for example, your mobile phone is telling you every minute or every 15 minutes about the energy consumption. So I would turn that off, that service. So there is definitely a limit of the frequency of reporting, despite the technical possibility to go higher there. But there is another thing. If you would get information about the appliance consumption, so the what is shown here on the slide was 12% real-time appliance level feedback. So you get information what your fridge has consumed, what your computer has consumed. Then probably you can uh, get a better understanding why you can save most of the energy. So actually so down there is a paper cited, and this was part of a research project. And in this research project, we also did measurements of appliance consumptions in various houses. And I also volunteered for my house to have basically all the major appliances measured there. And uh, by when I got after the measuring campaign was done, so I was not informed before because otherwise I would have changed my behavior, which would have screwed up the measurements. But after it was done, I got information that the device that consumes most of the energy in my household was not a fridge, not a heating device, not a boiler. No, it was a computer. It was a desktop computer, which we had the habit to turn it on in the morning. It was running all day because eventually checking some email or doing something with it. So it's running all day and at a good deal of the night as well. And this actually was my highest energy consumption. And after I learned this, I understood, okay, I just have to focus on this device. And it's very easy because there is a function that the computer goes to sleep mode if it's not used for some time. And this was just set in software. And suddenly I had reduced my energy consumption significantly. But somebody had to tell me this was the device that creates most of your energy consumption. So this project, we have done this with with measuring each device separately. But that would be a lot of effort having a lot of sensors installed, and they all have to report, and you have to gather this. So this was uh, not so feasible for a rollout. But there is the possibility to do it by analyzing your energy consumption and guessing or estimating which devices are running at what time. And this is called non-intrusive load monitoring, and this is a technology that is there, and it's based on algorithms, and it just needs data. There are, of course, privacy concerns, because if you have such a frequent measurement of power, it allows for inferring about your daily schedule. So whoever has this data knows when you got up, because before that you were typically not using many devices. When you get up, you turn on the light, you turn on your coffee machine, you turn on the radio. So a lot of devices are going on. When you leave the house, again, you are changing your behavior. When you come back again, or if you don't leave the house, if you stay at home, if you do the cooking, it's also visible. So we can see probably the daily behavior of multiple people living in a household just from the energy consumption. So this is something that we don't want to give out of hand. So this is definitely one thing, uh, but it can be used for good and evil. So just to show you how does uh, such a system or such a measurement look like, and here we see a power draw, an aggregated power draw measured at the smart meter, and you see here basically from 3 a.m. to 12 a.m. So one day, and in this case, you see that the person, something started already at 4 a.m., 4:30 a.m. Either it was the person or it was some automated device, but there is definitely a lot of activity at around 5:30. So let me just see if I can have a pointer here. So we see a lot of activity here. So this definitely somebody got up here and prepared themselves and left the house again at 6:30. So probably not a computer scientist because they would have slept longer. Uh, then there is another activity around noon. Some peak that goes on for like, I would say roughly 10 minutes or so. Uh, and then we have several activities in the evening. So with non-intrusive load monitoring, we are trying to disaggregate these power draws. So like to separate them back to their sources from different devices. And basically that would look like this. So if an appliance has like a power profile that is significant, for example, a fridge, if closed and set to a certain temperature, would cool down to the target temperature. Uh, this is this blue activity. Then stop the compressor. Then basically have almost no consumption. And when temperature falls, not falls below, grows above certain level, then it has to cool again. So we have these cooling cycles, and they are more or less periodical. So in this example here, you see that they are not exactly periodical. This is not a drawing mistake, but that could mean that, for example, somebody had opened the fridge, or okay, if it was open, then it should be closer. So here, probably the fridge was closed. But here, since it is like there is a time when it's restarting sooner, probably either the fridge was opened here or something at room temperature or even warmer was put into the fridge that caused the fridge average temperature to raise faster than necessary. So we have these things here. In contrast here, we have the dishwasher. For the dishwasher, it's assumed that there is like a heating cycle that goes for most of the time because we need the hot water all the time. So we have for some time this profile. And for the washing machine, we have it shorter than the dishwasher. Probably not to scale because my dishwasher takes like 3 hours for one load, and the washing machine like 1 hour. Uh, but the washing machine has more effort. Also, this is just an example. So real devices have more complex power draws. But just to show you this example, if you would add up those three power profiles, you would get something like this. And here it's still colored in order to see where it comes from, but it becomes clear even if this would be just an uncolored thing, it would be still easily possible to say which devices ran and what time. So we are analyzing this power consumption over time in order to find out what the different components there are doing. So here I added another device. So here is a baseload TV running all the time. So this is just an example. The actual algorithms, how to do this is a bit more complex, but the average ideas or the general ideas that you get the measurements from a smart meter at one central point, and from this you can estimate the consumption of the different devices. And so we split up the consumption to different appliances, and then we report this back to the user, and then the user would get an idea which devices were running at what time, which devices had consumption, had the highest consumption, the most significant contribution to your consumption, and which devices probably you don't have to worry about. And now for the algorithms, okay, what would be an appropriate algorithm? So there are different approaches to this. So this is a research field on its own. It's very interesting. So a standard approach would be to just model the different devices based on their average power consumption. Then just say that we look at the overall power consumption and try to find a set of devices that basically explain this power consumption. So this is known as the knapsack problem. So basically our knapsack is in this case the overall power consumption, and the things that we can put into the knapsack would be the different power values of the devices. And we try to find a set of available devices or a subset of available devices that matches the measured consumption as close as possible. The problem is, first, this is if you have many devices, it's a significantly large search space, which might require a heuristic search approach. And even more significant problems are that there can be ambiguous combinations. Like, for example, if you have one device with 150 watt and another one with 50 watt and another one with 200 watt, if you measure 200 watts, it's impossible to say if it was the 150 plus 50 or it was the one with 200. And there is also, since you always have whenever we go into looking at measurements, we never get exact values. So we always have some noise, some measurement errors. So we cannot be too sure that something is exactly the sum of this. And when we have like certain solutions, for example, here, we had estimated that there is the fridge running and the oven and what else? Some aero part, the stove, the microwave and the kitchen outlet. And the real situation was this. So it guessed several devices correctly, but the values are not the same. So we have this. And this system or this approach can also lead to the outcome that at one moment the system reports you that device A, B, F, and D are running, and the next moment it would report a totally different set. So, like if most of the devices that had been running before have been turned off, and now a totally different set is running, which is totally unrealistic. So usually you switch one or a couple of devices at the same time, but not all of them. So that's why the knapsack problem is not working well. If you want to know if a certain appliance set would work with the knapsack problem, then you need to calculate the a complexity value for it. And this appliance set complexity is something that you can calculate based on so this is now a problem of stochastic. So you have a certain power value, and around this power value, you have a given variance of the value. So different devices might have different variances, or the variance might also either stem from the device itself, so that the device itself has a power draw that is not always exactly as it's stated, or it can be a measurement error that is creating this variance here. And so if you have two measurements, there is a certain overlap that would make it difficult to tell if measurements in this overlap would belong to either this side or that side. With some very low probability, they could even belong to another one. So we can calculate these overlaps, and if you would model those things as normal distributions, which is quite an assumption, but unless we have further information about the distribution of the values normal distribution would do, then we can calculate the probability that we would mistake one measurement from one device for another one. And based on this, we can calculate the complexity value, and this complexity value would tell us how difficult it would be to disaggregate this. This is mainly for the knapsack approach, but since part of this knapsack ideas are also in other algorithms, the appliance set complexity is also something that is to be considered when modeling such systems and looking how well we could disaggregate them. If we consider that certain appliances that would cause problems are not always used, we could have, for example, if you have a value of 0, that's quite nice because then you can say, okay, no device is active at the moment. Because if I have 0 consumption, then I can be sure that no energy consuming or electric energy consuming device is active. So for 0, the complexity would be quite low. But if you have a certain value, then probably complexity is higher. Generally, we would expect that complexity would grow with the overall power consumption, which more or less is the case, but there are also some cases where a certain power consumption is quite unambiguous and can be disaggregated well. So here we see for the power draw, so we have here 6,000 samples over time. And here we see the respective complexity calculated for this power draw. So we see that complexity is going up and down, and complexity is not a steady value, but it's something that is defined over time. Of course, you can define a complexity value that would be the average of all the complexities per time unit. And then you basically take the average of this to define a total complexity. Okay, so far we know now that the problem is sometimes hard and sometimes easier. And we know one algorithm, but we have seen that the one algorithm has the problem that if we're going from one time instant to the other time instant, the algorithm does not take advantage of the fact that most likely if an appliance was on at the previous time instant, then it's more likely that it would be on again rather than that the device has changed its state. So using this information, we need some kind of modeling over time. And this we can do with a hidden Markov model. Basically, we would define a Markov process for one device. Let's start with one of those two here because they have just an on and an off state. So we have a certain probability to stay in the current state or to switch the device off. We have a certain probability to be off or to go to the on state. And in this case, we have a device that has not only one on state, but basically a second state that consumes more. So like 0 device is disconnected, 5 watts device is in standby, 1000 watt device is on. And so we have basically a state machine where the device changes between 3 possible power states, and here we have 2 possible power states. And then we have a certain probability. So over time, the device might change its state. For example, x1 being not the state of this device, and x1 at time t minus 1 is one state, x1 at time t is the next state, x1 at time t plus 1 is the following state. So we have changes with a certain probability, but we have more than one device because that was in the first place our our problem that we have more than one device. So we have uh, more than one device. And the problem is we cannot observe the individual devices. All we can observe are the sum of the power consumptions of those devices. So what we can observe is this Y here. And what we know is that the Y consists of several parts or fractions. And those parts, when modeled like this, would follow a Markov model where we have a certain probability for a state change over the time steps. So this makes it now a problem of solving a factorial hidden Markov model. And one possibility is to do this with a particle filter approach. We have done this. This is then called particle filter-based load disaggregation. Or, since it's easier to pronounce, it would be the PALDI algorithm, which we have then used. So it's not only us have done that, but there are other works also going for a hidden Markov model, basically doing load disaggregation like this. So this is the state of the art where you still understand the model, where the model is very clear. But you also see at the publication date here, this is 10 years in the past. What has happened in between? In between happened the deep learning approaches. So with a deep learning approach, if you have enough data, we have examples of the smart meter data and information which devices have been on or off. So you need a data set. If you have this, you can train a model, a neural network model, to classify based on the current measurement. Plus, typically there is a moving window of like the last n measurements that are taken. They are fed into the model, and then the model tells you which devices most likely have been enabled or disabled, being on or off, or being in whatever state for this given point in time. And uh, it's basically a classification problem which we would train using a machine learning approach. As long as we have a sufficiently large data set, we can do this. The results are quite nice. So of course, if you do machine learning, you always have to be sure that you test on a different part of the data set than you have trained with. So you would train, for example, if you have a data set that goes over 2 years, you would use 1 year for training. Usually the distribution between training and evaluation and validation is different, but just for simplicity, if you would have 2 years, you could use 1 year for training and then check on the second year if it works. And then you know, okay, we can achieve this accuracy. Then we can compare it with the results we get with the other approaches. And we see that the results excel. We can now detect, depending on the system, but for a typical household with 20 devices, like 90% of the devices can be explained using such a model. But the model is a black box model. So we don't know exactly how it does this. It's just providing it. Depending on the application, this might be a big problem or not. Probably since we only want to use it for giving feedback to the user, and probably if there is a slight mistake in the explanation of a device at some time, if it's not all the time, then probably it's not such a big problem. If a couple of watts too many or too few are assigned to one device instead of another device, this is probably something we can live with. So the black box model, something we can still use. And of course, we need the data set. So we have the problem that we need to train it, and we would need it for example, first we need to find a data set. Once we have this data set, we can train a model. And then still we have to be sure that the model that we have trained now also works with typical measurement data from other households. So this is a challenge because you cannot assume that if you have let's say you make a business model out of this and you offer customers to analyze their energy consumption on the level of devices, you cannot uh, ask the users first to for a full year to provide all their energy measurement data plus information when which device was on. Usually you don't have this ground truth in a in an application field. So this is a challenge to have this transferability of models. If you want to go into this, there is the nil decay system, which eases the setup of a nil experiment because the framework basically provides you algorithms. It also has a standard format for the data sets. Also, please be aware that since I talked about data sets, those are measured data sets. If you measure a data set for an extended time, for example, in a household, you always have not only measurement errors, but also a, a lot of situations where probably something didn't work, where the measurement system was down for some time, or there was no communication with one of the sensors. So if you look at real data sets, that giveaway is that sometimes you have these zeros or even empty measurements in it. Then you know, okay, this is a real data set that has been measured and not just fabricated, because we always have this. And then, of course, you need to be able to cope with these problems. So what do you do if there is a missing data point? Do you interpolate it or do you remove it from the set? But if you remove it from the set, then you have a different timing or time interval between two measurements. So those are the challenges you will face despite the availability of such tools. So it's still a lot of challenge, a lot of work to do it. Another goal. So this is something you could do. Could look for measurements, evaluate them, and then look into ways of looking uh, for basically using the same model in in a different household. Another problem is uh, if you have the household devices, and there are some devices, and you don't get a list of initial household devices from the user up first. So you don't know which devices are in there. So you need to kind of label the appliance events and find out what is running there. So you have typical household devices, but still they are not always the same. So if you would train the model on my fridge, most likely your fridge would have different patterns. By looking at the behavior, you'd be able to see it's still a fridge. But if the system can do this automatically, that would make also the system more useful. Another thing for the uh, for doing the disaggregation, we found out that values of, let's say, second granularity, so having a measurement every second, or we live it even a little bit higher than that, so like every tenth of a second or so, they would be great to like detect devices. But in the beginning of the talk, I told you that the smart meter has like interval measurements of like 15 minutes or 1 hour or something. So the question is, can we still use 15, can you use a 15-minute data interval to detect the usage of a coffee machine? So how long it takes a coffee machine to make a coffee? Hopefully not too long, hopefully not 15 minutes. Not going to wait so long for my coffee. So typically it's less than a minute where the coffee machine is active or makes your coffee. Uh, and then you take it, and after 30 seconds, the machine is back uh, to its standby state. So after this short coffee break, we continue. And conclude that we need different measurement intervals. And unfortunately, since the smart meters that have been rolled out, a lot of hardware in all the houses, uh, they are not built for making 1 second measurements and reporting them to the user. So we don't have this interface. So in order to really get the most out of this approach of non-intrusive load monitoring, uh, there would be the challenge of getting proper measurements. And for those measurements, you might want to look also into other measurement devices. And there is a market for this private smart metering. And those are measurement devices that allow you to measure the energy consumptions for your own applications. So either you can use them to measure particular devices, or you can use them to like monitor the your own energy consumption in total and then run the non-intrusive load monitoring algorithm in order to identify energy hungry devices. Could be also used to optimize energy consumption in your system in a smart home manner. Like, for example, having measuring also the PV systems production, optimizing it, providing features for smart homes and ambient assisted living. So there is a market for this. What you see here on the right side also, it looks very much self-made. These are actually products that you can get as open hardware. This is open energy monitor in this case. There is this market for private power meters. A lot of those things are still very much on the experimental phase, but there are open hardware designs that make it interesting to use them and to extend them. Would be also an interesting case for uh, doing some academic work on improving those or looking at such architectures or providing a proper measurement system. So also we have looked into this and we have decided not to build a measurement system with the microcontroller and everything, but instead of using something that is already well known and well tested, like an Arduino or a Raspberry Pi, and then uh, creating just a shield, since the Arduino and Raspberry Pis, they have those standardized interfaces. So basically you can make a piggyback uh, system that you connect to it, and this would do the measuring. So what you see here is an Arduino standard thing, and this is then, here are two examples of our measurement add-ons or measurement shields that are uh, measuring current and voltage and therefore also the power of systems. So we have 230 volts on these parts. So you have to be really careful and know what you're doing. And you also have a version with a case so that it's not possible to touch the lav wire. Uh, but was a challenge designing this in a proper way. So there is the need, for example, to separate the net voltage part from the electronic part, being sure that nothing goes back to the Arduino. So this is quite some design effort. But once we had it, we uh, provided it as with the software and the design documents as open source and open hardware. So the schematics and the PCB design are publicly available. For those, there is one for the Arduino Shield, and nowadays we rather use the Raspberry Pi version because with the Raspberry Pi we have more processing power and can already do part of the load disaggregation directly on the system. Unfortunately, this also changes the values for the overall parts cost here, because this would be for the shield, but if you would add the Raspberry Pi, then we have suddenly twice the price, probably. I think the Raspberry Pi is around 90 euros at the moment, if not even higher. Depends on the model. So with those. So we called our system everything together YOMO. So you measure only once, hopefully. We basically get information from the devices. We are measuring it. We are recording it. And with the Raspberry Pi, we can also run locally web server on it. So to provide the user a visualization and feedback on the current power consumption and the behavior of the different devices. Do you remember this slide at the beginning of somewhere at the beginning of my talk, where I talked about the problem of privacy? There were some things that were really a little bit disturbing. Like if somebody gets your measurement data, they would know when you get up, they would know what kind of devices you have, they would know about your daily living situation, everything. And now we have a solution that would work everything in-house. So if we're able to get these algorithms to a level where they would run on a Raspberry Pi, which of course regarding uh, the the computation power is much worse than you have with a computer. So if you have done some machine learning, then typically you know that Raspberry Pi is not a good platform for doing machine learning. But if we are able to get this on the Raspberry Pi, we would solve the privacy problem because everything would stay within the same system and the user would see their data, but it wouldn't go out to some server somewhere to be analyzed, stored, and whatnot. So this is also an interesting challenge in this field where we can provide a better system if we would further invest some research and our ideas and stuff. So what else? I already talked about the issue that we need data sets. And of course, we need those data sets that have measured the particular devices because we need the information about the devices to have a ground truth. And of course, if we want to apply them, we would expect that the geographic region where the data set was taken is similar to the place where we want to disaggregate. Because if you have a different geographic region, typically this also comes with different devices, different uh, frequencies of the AC power, different voltages, different behavior of everything in general. So this would be quite a problem if the regions and device sets are too different. Also, the measurement frequency of your data set should be at least as high as the measurement frequency that you're going to use on your system. You need these individually measured devices, and you also need a sufficient duration of measurement campaign. So would be good if you would span at least all 4 seasons, and if it's more than that, even better. Because it's very difficult if you just train your system with devices that have been running during the month of July, and then you try to detect the devices that run in December. You would have different devices in both cases, despite the case that it would be the same household. So we need uh, those data sets to also going for a significantly long duration. And also it depends, have they been measured households? What's the size of the household or apartments or office environment or industry environments? So depending on what you want, where you want uh, to put your system, you would have different requirements on the data set and you would look for other data sets. So what are example data sets? So here are some, I don't want to go into detail, but you see here on the last column, there is the resolution. So, for example, the first data set here has a resolution of 10 seconds. Since I said I would like to have like 1 second, so probably this is not the one easy to use. 1 minute, 12 kilohertz, more than enough. The question is, what about the duration? Is it several seasons? It's for 8 days. 8 days probably is not multiple seasons. So here we have one year. Forget this parenthesis here. It's already done now. So green D, this is a data set that we measured in some households in Austria and Italy. We had 9 houses. We have the 1 Hertz. We did not measure other features than the effective power. So some other data sets are more detailed on this, but at least we have the 4 seasons and we have the 1 Hertz. And with Austria, of course, we would have a data set that has the proper region if you want to deploy a system in Austria. If you want to go to a different country, you would have to look for other data sets. So for UK, for example, we have data set here. There is another one, UK daily. That one is nice because you have significantly high frequency. Okay, it's 6 seconds because the 16 kilohertz is for part of the data set, but 6 seconds still okay. And you have 500 days for 99 days. So we have those data sets. In case for your application there is no data set, what could you do? You could measure your own data set. For example, if you say I have a specific case with an office environment and there is no open data set that provides this data and I want to do it, then you need to go and do your own measurement. So we have done this for the Screen D data set. And this is like an example here. We've used such power plugs or smart plugs that go between the socket and the plug. Uh, and then have a Raspberry Pi device that is basically pulling the measurements there, saving them on an SD card, and then transmitting them. Of course, you have also to find people that are willing to take part in your measurement campaign in order to get this data. So those are examples of these power readings that we get there. So you see here over several days, you see different devices used. Dishwasher, coffee machine, TV. Okay, it's not several days. It's one day. It's one day from yeah, it's exactly one day, 24 hours. I was already wondering what a coffee machine is on just a couple of times. So where were those guys? They had 1, 2, 3, 4, 5, 6 coffees one day. So cannot be me. For me, it definitely would have been more coffees. Well, so this is like an overview of what NILM is, how NILM could be used to improve energy consumption by just telling people what the different appliances consume in particular. And we have learned about the basics about the approach, some algorithms, that the approach where we basically use a deep learning approach is the one that works best. But in order to do so, we need a data set. If we cannot find a data set, we need to measure our own. So there are certain steps to be done in order to be successful with creating or improving sustainability with computer science. But there is a way to it. And for all these parts, there is also a slide on references, which I'm not going to read to you now. But since the slides will be provided for download, you have some references to start with. So if you're interested in this topic, I would be very happy. And also you can contact me if you want to focus your research on this. And of course, please feel free to ask some questions now.